Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand you? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, and Chris Smith. Now, we've got lots of questions coming in, but what's new in the world of science, Chris?
This one caught my eye this week, Sue. Very exciting. Anyone who's got a dog knows very well that the dog is very good at knowing exactly what you want to do and when you want to do it. And that's because it looks like dogs have evolved to interpret human emotion. There's a researcher based at the University of Lincoln. His name's Kun Guo. And what he has done is to watch dogs as they watch pictures of faces and look at how long the dogs look at the pictures and the way in which the dogs look at the pictures. Now, why this is important is that there's a phenomenon amongst humans which is called left gaze bias, or LGB. And what this is all about is that if you show people pictures of people's faces, or if you get someone to look at someone else, for some reason, people will always look at the right-hand side of the person they're looking at's face first, and for longer. So in other words, if you're looking at yourself in the mirror, you would focus your gaze on the left-hand side of the image. In other words, your own face's right-hand side. Now, there's a number of reasons why this might be the case, because scientists have shown over time that the right-hand side of the face does seem to portray more emotion and might therefore be a useful giveaway as to what someone's thinking or how they're reacting to what you're saying. But also, the right-hand side of your brain processes everything that you see on the left. And the right-hand side of the brain is the part of your brain where you tend to process emotion and you also interpret emotion. And you also do visuospatial mapping, in other words, working out how objects move in space. So the right side of the brain is very well tuned up to understand facial emotion. And so it could be that that's why we look at the right-hand side of people's faces so much. But what about the dogs? Well, people wondered, well, are dogs the same? Because, of course, they're man's best friend. We've been co-evolving. We've been breeding dogs selectively for 10,000 years. So would that close association with us have rubbed off on dogs? And that's exactly what these scientists have found, that when you put dogs in front of screens with people's faces, the dogs are much more interested in looking at the right-hand side of the people's faces for much longer. They're not so interested when you show them pictures of non-faces, other animals, even other dogs, or inanimate objects. So it looks like dogs have evolved to study our faces and try and predict what we're thinking on the basis of our facial expression.
That is absolutely amazing. What fantastic research. Thank you very much for that. Well, we've got a few questions coming in. The first one comes from Agnes, who's in Braintree. And she says, what is the cause of Raynaud's disease? That's when your hands get really cold, isn't it, Chris?
Yes, Raynaud's disease is an interesting thing, which is, and I think I've got a bit of this, when you get your hands in contact with something very cold. So say you open the freezer and you reach into the freezer and you don't want the peas which are right at the front, so you take the peas out and you hold them in your hand whilst you reach in with the other hand to get to the back of the freezer. Meanwhile, your fingers are in contact with the cold peas. Very soon you get this intense burning pain in your fingers. They tend to become very cold and white, and then very, very painful. And then when you put the peas back in the freezer, then the fingers slowly warm up again, and then they throb afterwards. And this seems to be some kind of phenomenon related to hyperreactive blood vessels. So for some reason, our blood vessels react too abruptly and too strongly to cold or exposure to cold in people who have this Raynaud's disease, Raynaud's syndrome. And it is very, very painful. And in very, very severe cases, sometimes it can actually cause damage to the extremities, because the blood vessels can cramp down so tightly that they cut off the blood supply to the extremities, and this can sometimes cause damage. But it's more of a problem of discomfort than one of physical injury. But sometimes people find they get relief by taking drugs that open up blood vessels, and drugs including things like nifedipine, which is a drug which blocks up calcium channels, and calcium is necessary for muscles to constrict. So if you block the calcium channels, then the muscle can't constrict, and therefore your blood vessels stay open better. But that's the best we can do on Raynaud's, because we don't really understand why it happens. We know it's to do with cold-induced vasoconstriction, but we don't actually know why it happens, and we can't cure it, because in people who have it, they seem to have this written into them that they're going to get it.
One of those hereditary things then, I suppose.
Unfortunately, yeah. Well, you could always move to a warm country, but then you're still going to reach into the freezer for the ice, aren't you? So, yeah.
So what we have now, we've got an email. Disso, could Dr. Chris tell me why during the Black Death some people who were bitten by fleas and caught the plague survived, but most didn't? Was it something to do with their immune systems, and why did anyone survive at all? Good question. Chris?
Yeah, it is a good question, but it's a very hard question to answer because, of course, the Black Death was around many hundreds of years ago, and we weren't, so we didn't have modern medicine then, so we can't examine samples to see exactly what the Black Death was. What we do know about it was that it was a very vicious killer, and it wiped out more than a third of Europe's population very, very quickly. And it did so with devastating effect, and it looks like there were some people in the population that were more vulnerable and others who were less vulnerable. Now, prevailing wisdom about the Black Death is that it's a disease called Yersinia pestis, which is a kind of bacterial infection which can be spread by fleas which are carried by rats. And so one school of thought is that this spread around because rats were rife because of sewage and vegetation and mess and things that people made. This gave the rats a home, and the rats were able to spread the infection when they lived in cities amongst people. Thing is, though, that some people have criticised this theory because the dynamics of spread of this infection were inconsistent with a bacterial infection. It seemed to spread far too fast. In fact, it spread more like a viral infection. And this has led some people to suggest that, in fact, we've got it wrong. And, in fact, the Black Death wasn't Yersinia pestis, bubonic plague, but something else entirely different. And as a result, people have gone looking for what that cause might be. There was a study which was done a few years back where scientists went to a plague pit in London because where so many people were dying all at once, often dealing with the bodies was difficult. And what would often happen is there would be mass graves set up. Bodies would be dumped in the mass graves, and then the whole thing would just be covered over. Those plague pits still exist today, and they're well known in some parts of London where they are. And so researchers went to one of these plague sites, excavated the human remains, and they collected teeth. And teeth are very useful because they behave almost like a little sarcophagus, because if you drill into the teeth, inside, in the pulp cavity, you can find DNA. Now, if someone's died of an overwhelming bacterial infection, alongside the person's DNA, you should be able to find the bacterial DNA that killed them, because when someone has overwhelming infection, they've got bacteria spreading through the bloodstream to every tissue. When the researchers did this in these plague bodies and these plague pits, they were able to get human DNA, proving that they were getting DNA that could be copied and amplified, but they couldn't find any bacterial DNA. They certainly couldn't find any Yersinia pestis DNA. So this has added weight to the theory that the Black Death was a virus, not a bacterial infection. But then there's another question, which is, well, if it was a virus, what was it, and what's the evidence that it was a virus? Well, that leads us on to a new bit of research which has emerged more recently, and this focuses on a place further up north in England called Eyam, E-Y-A-M, where there's an excess number of people who live in that area who carry a certain genetic change or mutation called CCR5 delta 32. And CCR5 delta 32 also gives you resistance against diseases like HIV. If you carry this mutation, you cannot be infected by HIV. Scientists couldn't work out, well, if it wasn't a bacterial infection, what was it? Could it be a virus? And if so, what sort of virus was it? And an interesting parallel which has emerged is that there are people in Europe today who are very, very common. They carry a mutation called CCR5 delta 32. This is a gene which is expressed on the surface of white blood cells, and it's absolutely critical for HIV to get into cells. And if you have this delta 32 form of CCR5, then you are immune to HIV infection. You just can't catch it. And because there are so many people with this particular form of the gene in Europe, scientists wonder whether something back in history encouraged people who have that particular form of the gene to end up being much more common in the population than they should have been. And there's an interesting place in England called Eyam, E-Y-A-M, which has a very high proportion of people who have this particular mutation. And looking back in plague history, it looks like more people survived there than should have done by chance, suggesting that perhaps this CCR5 delta 32 was protecting people back in the Middle Ages in the same way as it's protecting people against HIV today. So how might it work? Well, scientists think that perhaps back in history when people weren't as mobile as they are today, because when we didn't have roads and cars, people were born in one particular area and they died in one particular area. So they married people locally, etc. So if they had one of these genes, which meant that they were resistant to the plague, for example, then it would have become concentrated in the local population. And this would have meant that there were hotspots where the plague did wipe people out, but then there would have been other areas where people carried these particular genes in their community, and that made them resistant, and so they all survived. This would have had the doubling up effect of also making that gene much more common in the population. So although scientists don't know yet exactly what the Black Death could have been, we still suspect it could have been a virus rather than Yersinia pestis, the bacterium. But history is still yet to reveal the secret of exactly what it was and also where it went, because come the mid-1600s, it vanished and we never saw it again.
Thank you very much, Dr. Chris. I understand a little bit more about that now. Andrew in Cambridge, he says his question is in regard to electrically remote-controlled helicopters. When a helicopter is in the air and it loses remote signal, it stays hovering stationary. Do they have a small gyro system to make this possible? Chris?
Yeah, helicopters are notoriously difficult to fly, but scientists are getting very good now at developing artificial flight systems so that you can have these unmanned aerial vehicles. In fact, they've been used in war zones, and they've also been used to do amazing research. There was a guy I spoke with a little while back who he had flown unmanned aerial vehicles into clouds, and then he had them hovering at different heights through clouds so he could detect the amount of solar radiation coming into the cloud, going out of the cloud, and how much heat was coming back up off the ground. And so he did some very elegant studies doing that. So these things are getting pretty good these days. The way in which they work, and helicopters are notoriously difficult to fly, is that they have accelerometers. They have the ability built into the aircraft to detect which way it's moving, and they have a very good computer system that knows how to compensate for movements of a craft in order to make sure it is stable. You have to write these programs very carefully, though, because if you're not careful, then you end up with it overcompensating and it goes off balance and crashes to Earth. So that's why you need engineers who are very good at writing computer programs that can damp problems like this. And I've actually got a colleague who I work with whose research is in fact on better steering systems for lorries. And you might think, how bizarre. But in fact, in order to get a lorry which can drive stably at speed and not have the back end develop a life of its own, you need some kind of special braking system and damping system to make sure that the lorry can steer itself out of these kind of resonant behaviours. And that's what he's developing. I think it's probably a bit similar to some of the programs you would need to write to control unmanned aerial vehicles up in the sky.
Good stuff. All right, well, we have a caller now. Our caller is Richard. Hello, Richard. You're through to Dr. Chris. What's your question?
Hi, Sue. Thanks. Hello, Chris.
Hi, Richard.
Hiya. Yeah, I've recently been to the Fitzwilliam Museum in Cambridge on a couple of occasions, and I've been absolutely amazed at some of the paintings that they've got there. One of the colours in particular seems to really sort of be so strong and leap out at you, and it's the blue in sort of medieval paintings, and I'm just wondering what there is about the pigment there that makes it so strong that you know it's the thing that really makes everything happen in the painting.
I suspect it's copper-based salt because copper salts do produce very beautiful blues. You get these sort of Prussian blues, if you remember. And there are also some other salts you can make with cyanide. There's a compound which, if you mix, in fact it's called Pearl's reagent, it's potassium hexaferricyanate. So you have some potassium and some iron and some cyanide together. And when these are oxidized, they go this beautiful blue colour. Right. So it could be that it's either something copper-based or it's one of these particular reagents. Usually things that are nice and brightly coloured are highly poisonous, in my experience. One of my favourite colours is the colour of cinnabar, which is a mercury compound, so mercuric oxide, and it's a beautiful, rich red colour. And the ancient Chinese were so impressed with it, and they thought, given it's got this beautiful blood-red lustre, that it must be good for you. So they used to make these life-prolonging elixirs out of cinnabar. They were in fact eating mercury, and of course they all went mad. But I suppose one benefit of that was that they were so mad they didn't know they weren't going to live forever, so they didn't care, they were happy.
Well, that's one way of looking at it, isn't it? Okay, that's lovely, thank you.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. More questions coming up this time for Dr. Chris. When you eat something very cold, says Brian in Daventry, what causes ice cream to give you headaches?
Yes, this is something that's pretty common, and it's something that I get a lot and very, very painful. You just have to hold something cold in a certain part in your mouth for too long, and you experience this splitting, excruciating frontal headache, which then goes as fast as it came. Where did it come from? Where did it go? Well, there's a number of theories about this. One theory is that it's a phenomenon called referred pain. Now, in the same way that when people have a heart attack or they have angina, there's not enough blood getting to their heart muscle, the pain of that is often felt down the left arm, up into the neck. It might go through to your back. It's not because you've got pain in the left arm, it's because nerves in the heart are getting irritated, but they don't carefully enough localise where the pain is coming from in the body to your heart. They interpret the pain as coming from a variety of areas on the body surface, and that's referred pain. The same phenomenon might be happening in the mouth, for example. The nerves that detect cold could be artificially and accidentally referring the pain which you're feeling from the coldness to the front of your head. Seems a bit tenuous though, and there's another theory of ice cream headache, which is instead that when you put something very cold in the mouth, there's a system in the head and neck which regulates temperature. And the nerves think that your mouth is much, much colder than it really is. And the answer is to warm it up by your body's natural radiator, which is to open up blood vessels, increase the blood flow through the tissue, and because blood is warm, it gives out heat, and this warms the tissue up to the normal amount. But because this is happening just in one small place in your mouth, but the effect is more global, this means that you get a painful opening up of blood vessels in certain parts of the head and neck, and this triggers the pain. It's a bit like a mini migraine, a temporary mini migraine. And of course, when the temperature goes back to normal, the pain goes away. That's probably the best I can do, actually, because we don't actually know precisely what causes it.
Thank you very much, Dr. Chris. Now, Mary has rung in to say Dr. Chris was talking about putting your hands in the freezer. She said she did it once with wet hands and screamed because it hurt so much. Her question is, can this be dangerous?
Well, if you put something very, very damp in something very, very cold, there's a danger, of course, that you'll get ice crystals forming on your skin and sealing or gluing your skin to the cold surface. And then when you take your hand away quickly, you leave the surfaces of your hand attached to the thing you were touching. And this does occasionally happen. There are some very, very cold surfaces, particularly industrial applications in industrial surfaces, when you touch something and you walk away and leave a layer of yourself attached to it. So yes, it can be dangerous. Thankfully, with the sort of temperatures you get in the average household freezer, unless you have very prolonged contact, and usually it's so prolonged that it's excruciatingly painful and you would have taken your hand away before then, this doesn't happen, thank God.
Our next question comes from John, who's sent an email in. He says, are there any dangers from the emission from all the fireworks that will be exploding between now and Christmas? There is a kind of mist in the sky after heavy sessions of fireworks, and you can smell them in the air. He doesn't think it can be very good for us. What do you think, Dr. Chris?
Well, I think John has got a point, and the reason that I think he's got a point is that if you look at how fireworks are made, they use a clever bit of chemistry which was in fact discovered by Bunsen of Bunsen burner fame about 150 years ago, and that is the concept of spectroscopy. What Bunsen realised was that when you look at a distant star, like our sun for example, you can spot the chemicals that are in the star because they have a characteristic pattern of wavelengths of light that they produce, and that's how we know what the composition of a distant star is without actually having to physically go and visit it. The same trick works on Earth. If you heat up a certain chemical, then it will emit energy, light, at a certain wavelength, and each element has its own fingerprint colour that it produces. Now that's how you produce fireworks, because we know what the chemical colours are, and so if you want a green firework, for example, you could use some barium, which produces a beautiful apple green colour, or some iron, which also under certain circumstances produces a green colour. So does copper. If you wanted a nice brick red colour, you could use some strontium salts, for example. When you heat them up and burn them, the heat from the flame excites the atoms in the chemical, and the excited atoms then emit photons of light at the wavelength that we see as whatever that colour is. The problem is that a lot of these things are heavy metals, and they therefore get into the environment when you burn them, and that could pose a health risk. But Disney in Florida have been, and also the one in California, have been having huge fireworks displays for over 20 years. And when I spoke to a man in Portsmouth recently who's a professional chemist and actually got into the Guinness Book of Record for releasing 40,000 rockets in about 3 minutes, about 2 years ago, he said that when he asked Disney, they had not detected any increase in heavy metal contamination in the water that surrounds the area where they let the fireworks off, having been doing this for 20 years. But I countered his argument by saying, well, that's because all of the heavy metals have gone home in the lungs of the thousands of visitors who've been going to Disney for all these years. But it was just a joke. So the answer is there's a theoretical risk, but I don't think it's a huge one. And I think the enjoyment of Bonfire Night far outweighs any health and safety-esque risks. And I don't want to spoil anyone having a good time. So go and have a good time.
Thank you, Dr. Chris. Right, it's time now to open up the phone lines once again, because we have Tony on the line. Hello, Tony.
Good evening, Maria.
It's lovely to have you on the show again. Another question for Dr. Chris.
There's a time lapse when we phone a long way away, like Iraq, say, and you can see on the television a person waiting there. So the correspondent in England says something or other, and he sort of, you almost see him listening to it. You've heard it. But then when it gets to the end of it, this is where it gets difficult to explain. He answers it, and we hear him right away. Do you get my point?
Yes, I do. And the reason, Tony, that you see this delay is because there is a coding delay in transmitting the signal from wherever it's originating from to the distant person. Yeah. And the visuals and the audio are transmitted side by side to make sure that they match up. Yeah. Because otherwise you'd end up with the person's mouth saying something at a different rate to what they're actually saying. Yeah, because the audio takes less processing. Because audio is very little data. It's very easy to transmit audio. It's much more difficult to transmit pictures. So you have to make sure you match the two up. And so there's a timeline which is applied to the audio, and there's a timeline applied to the visual signature, and they arrive in the processing, and the two are matched up so that the two are in sync. And this makes sure that people are speaking with their mouth moving, saying the right words at the right time, because otherwise it makes for terrible television. But it's very carefully coordinated, and if you get it wrong, then obviously it really affects the enjoyment of the broadcast, because you're thinking, this person's saying something completely different to what I'm hearing. But that's why you sync up the audio and the visuals together when they come back over to this side of the conversation, let's say. But it's all down to processing delay, because when you're seeing those kind of pictures, the way they're being transmitted is that the analog signal, in other words, the sound waves that the person's producing, the light waves bouncing off them, are going into digital equipment. They're being encoded as a digital signature, in other words, an electronic representation of what those sound and light waves looked like. They then get fired down a big piece of wire and also beamed off satellites and things. They come back to a studio, and then a clever decoder has to work out, based on that digital signature, how to recreate the picture that was originally at the other end. And that takes time, because it's complicated electronics that have to go on, and that time delay is why you see the person nodding for ages, and then about half an hour later they start answering the question. And if they try and interrupt each other, you get this horrible sort of telephone tennis effect until they decide who's actually going to go first.
I'm with you. Yeah, just about. It's not easy to understand. Thank you very much, Doctor.
Thanks, Tony.
Thank you, Tony. Bye-bye.
Bye.
Tony, another Tony, says, hi, Chris and Sue. I heard somewhere that satellites that are used by sat-navs are military owned by the US. I don't know how much truth there is in this, but I wondered if this means they could pull the plug at some point, or send you in the wrong direction, I guess. Chris, what do you reckon?
Yes, they are. And the sat-nav system that we use is funded by the US, and it is originally intended as a military thing. And when they first set up sat-nav, it was set up in such a way that for domestic use, i.e. non-military use, it added an error to the signal that you got, so that you could never be very precise. You knew vaguely where you were, but not exactly where you were. But military targets could be reached with precision. But in recent years, that was removed, and so now everyone has access to the GPS signal, which gives them spot-on positioning on where they are. But yes, in theory, if the US decided it didn't like the rest of the world, until we get the competitor system, which is I think there's a competitor system being plumbed in at the moment, actually, but until that's up and running, then America does hold the stranglehold. And in fact, the same is true of the internet, actually. The main name servers that control where all the website addresses are on the internet. In other words, it's a bit like the giant phone book, which controls where all the computers are and the addresses for those computers in the world. Those are held in America. So if America wanted to turn really nasty, they could not only enable us to get lost finding our way to the shops and back, because we've all become so reliant on sat-nav now, they could also stop us from ordering online as well.
It's all getting very scary. It really is. Well, I know that from time to time you get emails and things, don't you, to the Naked Scientists website. So what have you got to share with us tonight?
Well, I've got quite an interesting question from Simone. She's actually listening in South Africa, and she says, what's the answer to ridding the body of the bacteria that cause body odour? Where does it come from? How can we stop it? Well, the bacteria that cause body odour, usually we associate them with underarm whiffy smells, and the reason that we have underarm whiffs is because we have in that area everything that bacteria need to grow and thrive and flourish. What do they need? Well, they need something to eat, and we provide them with that in the form of dead skin, because every second our body's shedding thousands of dead skin cells. I think over every minute or so we're losing something like 40,000 dead skin cells, and if you added up all the dead skin that we shed in a lifetime, it weighs more than about 2 stone. So there's huge amounts of dead skin which is lurking in your armpits that bacteria can eat. There's also lots of water, because the sweat glands there, which are designed to keep us cool and also advertise us to the rest of the world chemically, they provide the bacteria with the water they need. And at the same time, there's also the other key ingredient, which is warmth. And when you put those three things together, it's a bacterial banquet that can take place. And the bacteria that live under our arms flourish and produce lots of side products of their metabolism, including some smelly ones. And these smelly chemicals are what make body odour. How do we actually stop these bacteria? Well, that's how antiperspirants work. What they do is to contain chemicals like aluminium hydrates and aluminium chlorhydrates and aluminium zirconium compounds, and what these do is to form a sort of gel which jams itself into the sweat glands, blocking up the supply and flow of sweat so that your underarm is kept less sweaty, and this makes it much harder for bacteria to grow, and that's how you end up with an antiperspirant effect. And they're also mixed with a sort of perfume, so not only are you suppressing the bad smells, you're also adding some good smells, and that keeps you smelling sweet all day.
Right, we got another question now, this time from Alan. He's sent a text in to say, can you ask Dr. Chris what causes or how do diamond, ruby and other stones, how are they formed? Yeah, I wonder about that. What's your answer, Chris?
Well, the answer is that diamond is different. Diamond is made entirely of carbon, and this is an amazing molecule if you look at it. So diamond is a giant molecule of carbon. If you could zoom in with a very powerful microscope, what you would see is an atom of carbon, and in a sort of tetrahedral shape around that carbon would be other carbon atoms, and each of those, there will be 4 of those, and each of those would be connected to 4 other carbon atoms, and this makes diamond very, very tough because all the carbon atoms are fully bonded to other carbon atoms, and if you pull it in one direction, you're pulling on all these other bonds, and it doesn't want to move, so it's very, very stiff, and as a result, diamond is the toughest substance we know. It's one of the hardest substances on the Mohs scale, M-O-H, Mohs scale of hardness, of which 10 at the top is things like diamonds, and 1 at the bottom is soft stuff like talcum powder. Now, the other precious stones, things like rubies and sapphires, in fact, surprisingly enough, all are derived from aluminium. They're salts of aluminium, aluminium silicate, so they're aluminium with some oxygen and some silica in there. And depending upon the conditions under which they're formed, usually they're formed under very high pressure and high temperature conditions. Usually that means hot springs, hydrothermal systems, volcanoes, that sort of thing. That will produce the right sorts of crystallization environments for the formation of these precious stones. And when geologists go looking for precious stones, they go looking in sites that they know had those right sorts of environments going back in history. So that's where you'll find those sorts of precious stones. But they're basically very, very regular and very, very tough, very tightly bound lattices of the different ions, the components that make up the crystal, and this gives them their strength, and also means that if you add other chemicals in here and there, you get nice colours. And so things like rubies and sapphires differ because they have other atoms mixed in with them which give them their colour.
Right. One last question then from your email list then, Chris.
I've got one here from Michael Burke, and he says, does photosynthesis add weight to plants? In other words, when plants are growing, when they're taking in carbon dioxide from the atmosphere and churning out oxygen, they're also, of course, absorbing sunlight. But is this adding weight to the plant? And the answer is yes, of course. The reason that a plant grows is because it takes carbon from the atmosphere and it fixes it together to make other larger molecules based around carbon, sugars, for example. These drive chemical reactions that enable the plant to make other molecules, and it translates into growth. So a plant goes from something small to something very big just by soaking up CO2 from the atmosphere. So part of that energy, part of that weight gain rather, comes from the carbon dioxide. Part of the weight gain actually comes, cleverly enough, from light, because Einstein told us E equals mc squared. E, energy, equals mass times c, the speed of light squared. So if you take energy out of sunlight, then you must actually get an increase in mass in return. So basically, yes, the plants are increasing in mass because they gain carbon from the atmosphere, and they also gain a little bit of mass from the light that they burn off, basically, to drive their chemical reactions.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.